Hi, Serena! Yay!
Hey, hello.
How are you?
Yay. I'm back. I'm ready.
So happy.
Mm.
We missed you so much.
Oh, I missed all of you so much too. It was just a maddening travel scene, but I'm back.
Perfect. Hi, Jamie.
Hey, hey, Jamie.
Hello, everybody. How are you today?
Great. Great, great.
Excellent.
This is a great one to come back to, too. Artificial 3D printed robot skins.
Sounds pretty awesome. I was thinking of attaching it to that robot with the astrocytes for the brain.
Oh, yeah, we got to hook organoids up to these things.
Yes!
Definitely.
I'm just going to ping people. I'm just going to share the room and stuff. Just be right back.
Well, we could maybe just put the skin right on them. Maybe that would be actually the first easiest to do input, no? I mean, skin is
Well,
pretty flat.
yeah. Well, I'm wondering if we could like scale little fingers down to very small dimensions,
Yeah.
and yeah, have complex geometries, and then feed those into them too.
Well,
That
we
would be
will
so
ask.
cool.
We'll definitely get those questions in.
Oh yeah, and little actuators, and they have like 10, 20, 30 little tiny fingers.
I don't
Cool
know why I
stuff.
thought of this. I don't know why I just thought of this, but could you imagine a toothbrush with tiny little fingers that cleans out your teeth really thoroughly? That would, I don't know why I just thought of something so weird. Oh,
Although, yeah, that's the whole angle, like medical robots, nanobots, and stuff that have articulated senses like that. Go in and do things at a micro scale.
would touch be a benefit to these things? If they're small nanobots and stuff, would they need to have touch, or would they just be able to be directed with either with a human or with camera detectors and stuff?
Well, it'll
Like,
be really
how would
interesting to
touch be?
see what the substrates are and what the limitations are, or if there's like general principles for different materials. That'll be really cool.
Because it mentioned like a biomimetic substance. Um, Biomimetic, is that like biological, but it can be shaped? Um,
Could be. It just means inspired from biology.
yeah, yeah, really interesting. It's the kind of, because I said in even the paper, but I was reading about how like AI is developing to the point of like animal behavior. We can program with animal behaviors and stuff like that in it. Um, and like giving it touch as well. I wonder if I could see like robot pets that we couldn't really tell weren't robot.
Well, I imagine we need astrocytes in the loop to get there.
Oh yes, 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 absolutely. And it actually would be really interesting, right? Because they might respond to like a tactile um, feedback from outside.
What you mean with the organoids? Hi,
Yeah,
Sarah.
yeah, because like a
Mm-hmm. Well,
yeah,
at some point that's kind of the interesting question because they are it is human brain tissue. So we kind of know at in its full on natural state that's certainly what it does.
yeah,
But how much do you get for approaching that incrementally? It's going to be pretty fascinating.
yeah. possibilities are kind of wild. Yeah.
Hello, Cicerium. How are you?
Hi, Susan.
Hi everyone in the audience. We'll start in a few minutes. Will be really interesting to learn from Professor Nathan Lepore. He's at the University of Bristol, and he is a professor of robotics and AI there. Maybe in the meantime, I can rather share his lab website, pin that on the top for people who are interested in his work. There we go. And yeah, we will start soon. It will be really interesting. He is really, he did some really interesting breakthroughs, and will be great to learn from him. Thank you for coming. I mean, the skin part is really, I guess, to improve maybe surgeon robots and everything that needs like really fine-tuned motor skills. And then also for people that have disabilities, what I think is really interesting in that regard is, previous Miguel Nicolili's lab where he built exoskeleton for paralyzed people. And the really surprising outcome was not just that paralyzed people could, without invasive technology, gain control of over the exoskeletons by using like sensory input into the arms from like the surface, but then also regain some abilities to control muscle movements and stuff. Hi Nathan, there you are. How are you today? Thank you for coming.
Hi, Nathan.
Hi, Nathan. Welcome, Doctor.
So the to unmute, it's all the way on the bottom right corner. There's a little microphone symbol. If you press on that, we can hear you.
That's got it. I was saying hello to everyone. Didn't realise I was on mute.
There you
Oh,
are.
there you
There we
Hi,
go. We
go.
can
welcome.
hear you now.
Hello.
How's your Friday? I hope everything went well. I know it's late it's the same time zone Jamie is in. Jamie is from Scotland,
Yep.
so.
Oh, cool. Yeah, no, I've had a good day. I haven't had many meetings today, which is always was a good day, I'd say.
Oh, that's a great day.
Usually my days are full of meetings. Yeah. So how do these things work? I have to be honest. This is a bit strange for me. Doing a meeting like this.
Okay, yeah, let me give you a short overview. I'll also put back your presentation back up so that you'll see it. Yeah, so we will start in a few minutes. I'll give like a short introduction about yourself, and then one of us will ask like a couple of general interview questions, like why are you in science? What happened to you? Like, they will be way nicer. I just say it that way because,
I'm happy if you say it that way.
I love the framing, Katarina. What
Yeah.
happened to you?
Yeah, like, what are you doing here?
I won't be offended, whatever you add.
And then about your current field, like, why you chose that field. We think it's kind of interesting for starting career people and general public that want to know more about
Yeah.
the science world. if that's okay with you. And then it would be time for you to present, like the presentation. If you check on top, like above our heads, there should be a link. And this is
Okay.
how the audience will see it. So they have to scroll through the presentation themselves. So it's really helpful to say, now I'm switching slides, and maybe even mention the slide number. That's really helpful. And yeah, and then we can open up for questions. And yeah, it's supposed to be fun. I hope you'll enjoy it.
Yeah, it's different. It's nice to try something different out.
Yeah, the cool thing about this is that it's a public room. So everyone that sees the title in the hallway can join. It will appear more for people that shows like they're interested in science, maybe in AI and robotics. And it's very interactive, right? Questions.
Cool.
So it's a little bit different than a podcast because you can just interact and kind of get to know the real scientist a little bit and ask questions.
Cool. So basically, I mean, I'll do it as a normal talk because obviously I don't know how to do anything else. But I'm really, if I get interrupted and people ask questions, I'm obviously very happy with that.
Okay, perfect. Yeah, that's good to know. That's perfect. We'll start in around 3 minutes. Hi, Chris. How are you today? Welcome.
I am just fine. A friend sent me the paper there, and I was fascinated. I wanted to learn about some of the cobot programming and some of the joys you've been doing at the Touch. That's absolutely fascinating work.
Cool. Yeah, well, please, I say, just please guide me as I go. If I'm going off on a tangent, or you want to ask about anything, so I'm happy to just treat it more as a chat.
Honestly, because you're the one doing the talking, if you go on a tangent, it's because you feel it's important to share it. So we're listening. We're here to come on your journey. So
Okay.
This is Club's
Cool.
house. It's made for tangents.
Yeah, we're very tangent friendly.
So how often do you do these then? Are these like weekly? Is it weekly events? You do these?
Well, Katarina's a bit of a force of nature, and there's been times where daily we've been able to sustain daily
Wow.
presentations with guest speakers and variety of topics, and we love to get off into the technical weeds too. So
it's
great
not
Wow.
even
stuff.
epic. It's not even crazily rare to have two in a day. That's happened several times, and they've always been different topics and always been absolutely mind blowing. Katerina brings in an amazing selection of incredible people, which we're very very pleased that you're one of them.
Well, thank you. Well,
Clubhouse quality is all over the map, but Katarina's rooms are always some of a real treat. So we're really grateful that you could come here and share some of your knowledge with us, Nathan.
cool. Well, thank you.
Well, thank you. Thank you. That's so nice. Oh, thank you first. Hi, how are you? First, did you know that we have gifts now and like we can share like thumbs up and stuff like that? I'll show you. I just learned
I
this
just
week.
noticed, yeah.
Oh,
First
you
was
did?
first was sporting one, and I was like, oh, I didn't know Clubhouse could do that yet.
And even gifts. So, well, I
Oh,
didn't
that's so
know.
cool.
I
There's
got
mine.
teased giving an onboarding meeting.
Can you see mine?
How do you trigger them?
You double tap and hold on your
On your
on your
okay.
own picture.
There's the Friday gift for not having meetings on a Friday. I feel like we went to like 20 years of training and then we have meetings all day.
Yeah, I know exactly what you feel. It's weird, isn't it? As a scientist, you kind of think, you kind of think beforehand it's all like being in the lab or fiddling with technology, but in practice, it's sitting in meetings.
and talking about regulations as they, if you use
True
them,
research.
especially in biology, like, we want to order a new type of virus. Okay, we need to get 100,000 regulations. Anyways.
Absolutely, like fill in the million forms before you can get anywhere.
And then,
That's how science
yeah, and then
happens.
lawyers.
Yeah.
If you ordered from another lab, they are lawyers, and like, anyways.
I'm sure you probably just hear blah blah blah, no killer robots, blah blah blah.
Why does everyone always insist on the no killer robots? I mean, don't they know we're trying to do science here?
Party poopers.
Well, and then in the next phrase, you hear talk about Skynet. So
What the crazy part is there's labs where it's like, all right, guys, so guess what? So we told everyone else you're not allowed to do death robots. You're the death robot crew. You've got infinite funding. Do whatever you want. Just don't tell anyone, okay?
then you
Well,
get
it's seen
labs
as
saying, "No,
defense.
we're the Skynet group. We're the Skynet group."
It's seen as defense to do that research. You say because you're trying to anticipate what might happen to you, so you do the research to create the technology. It's kind of crazy, but I've heard of these kind of arguments being put forward.
And
Yeah,
then you work backward and you go,
that's a
what do you
little
need to
day
ban that?
jobby for me. But yeah, it's now AI is making great inroads, as you can imagine, in
Yep,
defense. It's sort of like the new battleground.
And what's more important is they can dance
absolutely.
and it can draw pretty pictures. And then, so regardless of what kind of conflict we have in the future, we know there'll be great artwork for it. That's the important thing. So Skynet will be able to memorialize us and have great dance moves from it.
Yeah, the artwork gets cleared
Oh
for
no.
publication.
You're not talking about an AI version of Footloose or something, are you? Please no. Just no.
I won't be talking about that today.
Okay, I think we can start. We can officially start. We can now start at the fun part first. I'm just chatting. Okay, welcome everyone to the Science Society, and a special welcome to Dr. Nathan Lepora. And before we start, let me give you a short overview. Dr. Nathan Lepora is a professor of robotics and AI at the University of Bristol, and he received an AI Leverhulme Leadership Award, and he did his at Cambridge University, and his PhD in theoretical physics in 1999. And later on, he was a lecturer in robotics in the Department of Engineering Math at the University of Bristol, and a reader in robotics. And then from starting 2019, a professor in robotics and AI. And Dr. Nathan Lepore is an academic that has a lot of cross-disciplinary interests in robotics and neuroscience. And his main focus in his research is on robots that have to create robots that have a human-like sense of touch and manual intelligence. And it's currently, he says, an exciting area to be in with a lot of progress. We are very honored to have you here. And before you start with your presentation, maybe Cecilia, him, and Jamie would like to ask you a couple of questions before we go into your talk. Thank you.
Okay, brilliant. Oh well, thanks for the nice introduction, and thanks everybody who's here having a listen as well.
Excellent. I can kick us off then. So first of all, welcome to Science Society officially. It's great to have you here. Now I'll start off with the first question. What point in your life did you actually find yourself being fascinated by science? And is there any special story to that you can recall that you can share with us? Thank you.
That's an interesting and difficult question. So I guess the question is why am I now a scientist? So I didn't take a very conventional career path because as Katrina was saying, actually my training was first as a mathematician, and then I did theoretical physics for my PhD, and I also had a research fellowship in that for a few years. Whereas, and then basically I had a gap from academia for several years where I worked as a writer, and then I came back and I was looking at what would be so there at that time. I guess was when I reflected about what I would like to do with my life, and kind of decided that being a scientist was what really motivated me and interested me. So I kind of had a choice. Then the question was what field to go in. When given I got a background in maths and something like theoretical physics, which is fairly useless for practical application. So I thought first of all computational neuroscience, that really interested me, get into how the brain works. And then from that they kind of evolved into robotics because that's just kind of the way the opportunities came. I don't know. Does that answer your question? So a bit
Oh,
of
very
planning and
much
a
so.
bit of luck.
Yeah, no, that's fascinating. I love how you're talking about how you tried to link it to your maths as well. So you were always still interested in mathematics, right? You just wanted to try and reach out into something where you could apply it and learn other stuff as well. Yeah.
Yeah, yeah,
Mm.
because that's kind of what I was kind of good at. In my degree that went well, and my PhD. So it's kind of given those skills, and if you want to be an academic, then the question is, what is there that you can do? And I guess the answer is you can do most things. Because most, obviously, science, maths underpins most sciences, and also the ability to solve problems. Which is ultimately what a maths degree is about. It's about problem solving.
Yeah, absolutely. Tusa Rahim, do you want to take the next question before we get started? Are you there?
Oh,
Just
I
have to.
think she's on other work meeting
Okay.
at the same
Oh,
time.
okay.
Sorry, I
I'll
didn't
just.
really.
No problem. Okay. Then last question then. So what is it exactly the story that's led you up to working on what we're going to be talking about today? How did that get your attention? How did you start working on it? And how was the journey for you before we get started?
Yeah.
Thank you.
Yeah, so I guess why did I end up working on trying to create artificial tactile skin? I guess is the question, and so I say it wasn't a linear path for me at all. It was kind of what opportunities came along at different points of my career, what seemed like the next natural step to go on. So I was working in computation. I went when I returned to academia as a postdoc after I'd had a break for 5 years or so from academia. Um, I was interested in modeling the brain, understanding how the cerebellum or basal ganglia, work in terms of computational modeling of them. And then um, basically I was working on the cerebellum at first, and then I moved to another research group at my institute, um, who was working on models of how how rats perceive using their whiskers, and doing neuroscience models of that and linking that into robotic models of whiskered robots as well. So it's kind of like you're trying to understand how the brain perceives the world using whiskers, and then you're trying to build that perception. You're trying to test that in a robot. So that was a fantastic project that I was on for a few years, and then I was kind of thinking to myself, what do I want to do as my own career? I was working as a postdoc there, and I was approaching like time to get a permanent position, become a lecturer, and so I thought, well, I could take the knowledge that I have about neuroscience and tactile sensing with whiskers, but I could apply it instead to robot hands and human like robot hands and human like touch, because I saw it as a more impactful problem. Because basically, if you can get robots to have the capabilities we do with our hands, then it's a grand unsolved problem in robotics. There's just an enormous range of applications that you could do with that technology. So I thought that was an interesting, both scientifically interesting and an important area to work in. So that's why I moved into it.
That is an absolutely fantastic lead up. Thanks very much for sharing that with us. Now you've whetted our appetites. The stage is yours, and please, when you're ready, let's. Looking forward to hearing your talk. Thank you.
Okay, brilliant. Well, thank you. So I've got my slides. I will try to guide through the slides as I go, but I appreciate some people may not fancy staring into a screen, so I'll try as well to keep it kind of independent slides, and also just interrupt me anytime. I mean, we were discussing this earlier. I mean, this is for the audience, and so in a sense, the audience can decide where this goes as well. So artificial 3D printed skin that feels. That's what this presentation's about. Say, my lab, we both create artificial skin, 3D printed skin, and we try to impart that skin with a sense of touch that has the same that has a similar functionality and capabilities as human touch. That's the goal. Okay, so why is human touch important for robotics? Well, so the human hand has been honed by millions. So this is slide one, but slide two. So the human hand has been honed by millions of years of evolution into a general purpose manipulation device, and nothing else comes close. And from my kind of hand-centered view of humans, then I really see our hands as kind of what makes us human. Because with our hands we've created technology. I mean, technology is basically stemmed from devices we originally made by hand, and then there's been this kind of cycle of technology where that those devices that we make have become ever more complicated and sophisticated. Until now we've got computers and and so on. But it all stems back to stuff that we made with our hands, and the intelligence that we had to use our hands in that way is what led to technology and all the good things and bad things that came with it. So so it's a big problem in robotics so if you could have robots that can have the capabilities we do with our hands, there's many kind of useful and societally important things that they could do, from sorting through our recycling, so that we become far better at recycling our materials, to doing kind of boring jobs that people don't want to do but currently have to, to like more efficient farming. So it could be, in principle, if it was a solved problem, it could be like a new industrial revolution where the automation could really come on strides and be able to do many things that currently can't do. So to do that, I think we should look to the human hand to design and deploy robots that are capable of human like dexterity. And the key aspect of how our hands work is having a sense of touch. Our hands are useless without a sense of touch, and our sense of touch is exquisitely detailed. You can almost think of it as like an eye in each of our fingertips in terms of its sophistication of our sense of touch. So that's why if you want to have robot hands that have the capabilities of human hands, those hands will need to have a sense of touch that is as good as the human sense of touch. So when I was asking myself, when I was moving into this area and looking into building up a lab, I asked yourself, how do you get a lab? What capabilities does a lab need to develop novel robot touch? So it's kind of tough because it's a very interdisciplinary area. I mean, it's a completely unsolved problem as well. And if you want to do it in a way that draws on biomimetics and biology, as I do as well, it means you have to be extremely interdisciplinary. You can't just view it as an engineering challenge, but you have to kind of view it as a kind of but you want to take biological knowledge and expertise as well. So you'd kind of combine soft robotics, AI for the intelligence, neurophysiology for how touch works. You have to build these things yourself as well because you can't buy them off the shelf. have to know neuroscience, a bit of neuroscience, how a brain interprets touch, and you also have to know traditional robotics as well, robot control. So it's kind of a tough problem, and to do it, it's not something you can do just as kind of one person. It's meant, or even with a small group of people, because all the skills are so varied. So you need a very diverse group of people, and a medium-sized lab, which are gradually built up over several years. And so this is slide 4 is a picture of my lab, 2020. I've been in the area for 5 years or so, and you see there's a kind of diverse group of people because there's a diverse set of interests, which is really important for giving that kind of span of viewpoints to tackle this problem, and makes the work more interesting as well if you have a kind of a diverse group of people around you with different perspectives and different opinions and different ways of looking at the problem. Okay, so the core technology that we use in our lab is called the TACTIP, BRL TACTIP. I didn't name it. I don't particularly like the name, but that's the name that stuck. TACTIP standing for tactile fingertips. So the technology was developed in 2009 by Jonathan Roster, who's also at the same lab as me, but kind of, if you like, is now working on different things. And I picked up this technology, as I say, about 6-7 years ago, and then kind of I've been driving it forward with my lab. And what makes it so that tactile sensing is a medium-sized area in robotics. There's maybe 100 people in the world, a couple of hundred, maybe 50 PIs, couple of hundred people working in the area. So it's small, but it's medium-sized, but nothing like, say, AI, which has like tens of thousands of people working in it. And our kind of unique selling point is our tactile sensor is combination of it's soft, so that it's kind of got a squidgy feel to it, which is important because our fingertips are soft as well. Now it's also optical, so it has a camera inside it, and I'll come to why this is important in a minute. But basically, that gives a high resolution tactile sense. And our own tactile sense is high resolution as well. We have thousands of mechanoreceptors spread across our fingertips. And then the other kind of our unique selling point, it combines soft and high resolution with biometric. So we try to copy how human skin functions. So we can say it's soft, biometric, and optical. They're the key features. And then an innovation we brought into the technology is we 3D print the skins as well using multi-material 3D printing. So on slide 6, you can see that the multi-material 3D printing has enabled us to rapidly innovate and progress the technology, because you can go through quite a quick design cycle with something that's 3D printed. And has also now enabled us to, make it in different shapes and sizes. And I even went back to whiskers again. At the top right here, you can see there's a kind of whiskery version of it, because that's an area I used to work in. Probably the key development we've made, I would say, is to get it down recently in terms of the hardware, is to get it down to the size of a human fingertip, which you can see in the kind of the anthropomorphic hand that's in the middle, in the central row to the right. There's a human-like hand there, and actually one of those fingertips uses this technology, and say it's down to the size of a fingertip. Which I think, in terms of high-resolution optical tactile sensors, we're currently the only lab that has miniaturized it down to that size at the moment. And then the kind of things we do bring AI into the research. So I'm going to come onto the paper in a minute, but I'll just give them the kind of feel for the span of work we do in my lab. So we do bring AI into the research as well, and there the goal is you want to be able to interact in real time using a sense of touch to control how the robot interacts with objects physically. So tasks like, for example, we might effortlessly just run our hands through our hair without thinking about it, but it's actually quite a complicated control task to do that from a robotic perspective. You have to basically use deep learn. We were only able to get this kind of control using deep learning methods, kind of advanced AI methods, and combining it with conventional control. There's a couple of videos linked to on slide 7 if you want to see kind of examples of the kind of control that we get. And then the way the field is going forwards is AI is really hitting this technology, so that you've got, at the same time as the tactile sensors being innovated and say becoming high resolution, having all these other good properties, AI is hitting the field as well. So the kind of techniques that were developed for computer and robot vision over the last decade are now coming into robot dexterity, and causing the field to develop quite rapidly. And one of the principles that we've worked on and seems to be becoming dominant in the field is to use reinforcement learning methods. So, say the kind of thing that DeepMind do in training AI agents to beat human players at Go or Atari games. You can use those same reinforcement learning methods to learn how for a robot to dexterously interact with the world. The problem is, if you're trying to learn those things in the real world, you basically need too much data. It's not possible to learn these skills in the real world, because when the methods that DeepMind developed for learning how to beat human players at Go play billions of Go games, which you can do in simulation, but you can't do that in reality. So the methods that are coming in are you learn how to map from the real world into the simulation, and then you can do the learning in simulation of how to do the dexterous interaction and kind of map it back to the real world. So these are some of the methods that we've been working on as well in our lab. That's kind of the state of the art of the AI. Okay, so that's, if you like, the kind of background.
Nathan, I was just going to ask if this is okay. When you're talking about taking in experience from outside and then put it in a simulation, is that like this stuff would maybe touch something and then the simulation would run inside its head in the same way that I would feel something and then my brain would decide where I should feel next, like that? So to try and kind of learn faster? Is that what you mean?
Yeah. It's so, suppose you want to learn a skill. You want to learn how to, I don't know, pour a jug of water into a cup or something. Or imagine a baby's learning how to handle objects, stack blocks. So if you to use the kind of methods that say DeepMind use, the kind of these revolutionary methods of reinforcement learning, I say you'd need to do that millions of times for the learning to converge, which is just not practical in the real world with robots. So what you do instead is you have real tactile data that you measure from your fingertip, from the artificial fingertip, and then you have a simulated tactile sensor, in the simulated world, and then what you can do is try to collect that same data in the simulation. So you've got a pair of collected data in reality and collected data in the simulation, and then that gives a map from kind of reality into simulation and simulation to reality, but just on pairing up the tactile data. And then in simulation, you can learn any skill. You can have a simulation of stacking blocks, or physics-based simulations are really easy. That's what computer games do. So you can simulate these things, and then you can learn how to do these things in simulation, and then so you can bridge back into reality afterwards by these methods of sim to real.
Absolutely fascinating. Thank you for answering the question. Thanks.
Yeah, I think it's going to become one of the dominant techniques in this area in the next 5-10 years. It could be transformatory. And it's kind of a weird way of looking at it, because you're kind of creating these simulations of the world, and then learning how to interact with in the simulation. But then, as I say, you can just then, once it's learned, you can just map that straight back to reality, and it works first time on the robot. And at the moment, it's only kind of basic things they can do, like feel around edges and kind of surfaces and stuff. But that technology is going to advance. But a bit of tangent. It's a bit different from what we're going to talk about, which is the present work is on this kind of biomimetics of touch. Our artificial tactile sensor that I would like to work in a similar way to the human sense of touch, and the work that we did on that, and particularly this is work done by Nick Pestle, who was a PhD student with me, for several years, and what he did is really connect together knowledge from biology about how our sense of touch works with the use of our robotic artificial skin, kind of showing there's this kind of you can get a match between how a sense of touch works in biology and how this artificial sense of touch works. So that's what he did, and we published it in 2 papers recently, both in the Royal Society Interface, pair of papers, um, and and it's about artificial afferent tactile sensing. So basically, what afferents mean is they're the nerve endings, if you like. They're the mechanoreceptors in the skin. So we're kind of saying artificial mechanoreceptors um, within these, as I say, these artificial tactile fingertips. So to give a bit more, we were very lucky with this work in that, because it was the first time that that group had compared an artificial tactile sensor to like the nerve signals coming from real skin. So it's both the first time it had been compared, but also the first time that a match had been found, and we did find a close match, as I'll come to in a minute. So we did a press, of course, because we've got papers in the Royal Society as well. They have a very good press team, so we put out a press release, and it kind of just ignited, and we recovered like hundreds of places covered this story. So we were very lucky. And it's first time it's ever happened to me that we got such a lot of interest in our work, which was fantastic. In many ways, I learned a lot actually myself from the kind of feedback I was getting when I was reading the articles that other people had wrote on our work. I learned a lot from that myself. So that's slide 10. I'll try to speed up. So I think so. So the inspiration from the work was in the 1980s. There were some classic papers on how our sense of touch works, where they were looking at basically like monkey fingertips feeling different patterns, such as like gratings and gaps and bars and edges, and they were measuring from the neurons coming from the fingertips and mapping that back to how the shape of the stimuli. So doing a relationship between the nerve signals coming off and the shape of the stimuli, and there was these couple of classic papers also published as a pair early in the 1980s, and that was really a kind of motivating point for us to kind of replicate those studies with the artificial tactile sensor. And then we also took inspiration from other work on robot psychophysics that came out a few years back, but didn't go as far as looking at the comparing the nerve signals, but did kind of make this point that you could do like psychophysics of robot touch. So that's slide 11. So now in particular, so the key biomimetic feature of our fingertip, our artificial fingertip, is in slide 12. You can see there's at the bottom right there's like a cut through of human skin, and basically between the top kind of outer stiff layer of skin called the epidermis and the inner softer layer of skin, which has got like the blood vessels and the mechanoreceptors in it, there are these structures, these called dermal papillae, which are kind of like lots of kind of rods protruding from the epidermis into the dermis. So lots of papillae kind of interdigitating between the two layers in quite a complex structure. And it's known that the mechanoreceptors in the human skin are found, the shallow mechanoreceptors are found near those dermal papillae, so which indicates that those dermal papillae play a role in our sense of touch. But it's not really known fully how they play a role in our sense of touch. So some people have proposed that the movement of those papillae is what is picked up by the mechanoreceptors. But I say it's kind of still an open question in the biology. So, and what our artificial tactile fingertip does is we 3D print those same papillae structures, which you can see in like the bottom slide here, the bottom right of slide 12. We 3D print those papillae structures, but instead of using nerves to pick up the movement of them, we use a camera and we put little markers on the end of the papillae, and then the camera picks up the movements of the papillae. So we treat that movement of those artificial 3D printed papillae is the nerve signals that come out from our artificial fingertip. That's what Nick did in this work. So to give a bit, I'll quickly skip through these time, but to give a bit more information about mechanoreceptors. So mechanoreceptors are the sensors in skin that respond to mechanical stimulation, i.e. movement. There's basically 4 types in human skin. There's what's known as shallow mechanoreceptors, of which there's 2 types. One feels sustained contact, so like constant pressure, so they're called slowly adapting. And then there's a second population which feels changes in contact, transient contact, which are called rapidly adapting. And then there's also 2 types of deep mechanoreceptors that are found much deeper down. So they're not near the papillae, but they're deep under the skin, and they kind of feel vibration and stretch. So that's kind of the biology of human skin. And then they've got various features like the shallow mechanoreceptors of small, high resolution. They're kind of like there's a high resolution sense of touch. They have small receptive fields, and they're quite dense. Whereas the deeper ones that feel vibration are kind of a low resolution, the more sparsely populated. So that's slide 14. Slide 15 just shows some examples of firing responses coming off them. So that these slowly adapting mechanoreceptors which feel constant pressure. So they fire reasonably constantly when there's pressure happening, and then turn off when there isn't. Whereas like the rapidly adapting mechanoreceptors which feel changes in contact, they fire rapidly when the change in pressure is happening, but then stop under constant pressure. So they're kind of signaling changes. So our model that we did to try and get these kind of artificial mechanoreceptors in our 3D printed tactile fingertip is basically we tracked the motion of the pins from the markers on the end, and we just used some simple computer vision to track. We kind of have the images from the camera look like lots of spots, like a kind of polka dot pattern from the markers on the ends of these papillae, and then as the skin indents, those papillae move. And we track the dots, the spots on the end of them with some computer vision algorithms, and then get out signals of how much those papillae displace, which we just treat as distance that they move. So the slowly adapting activity, so the sustained activity, we treated as just the displacements, and the rapidly adapting activity we treated as the velocity of the displacements, or the speed of displacements, how quickly something moves. Because if you put a constant pressure on the sensor, the tips will move and then stay still, and well, that's kind of like the sustained activity. There's a constant displacement happening. Whereas as they move, that gives a transient signal, which is kind of like the rapidly adapting activity. So that was our model, and then basically we reconstructed the data, if you like, these kind of artificial SA, slowly adapting and rapidly adapting mechanoreceptor activity, as if they were neurons. And then we measured it under, I say, the same experiments as they did back in the early 1980s. So one is a constant press onto a plate and then releasing it. And so slide 17, you see the artificial mechanoreceptor activity here. So this is for the artificial one, but if you look at plots of what it looks like from humans, from real skin, measuring the nerve signals, the rate of firing, they actually look very similar to these. So this looks very reminiscent of real recorded data from real skin. So that's a response to pressure. Now the key response, kind of the smoking gun, was this experiment 1B, which is using grating stimuli, which are kind of like so slide 18, and so these are kind of stimuli which are made from like ridges and then gaps between those. So these are gratings, and these are aperiodic gratings, so they're varying the distance between the ridges, and then what they did in the early 1980s is that they looked at how strong the neural activity was coming off the fingertip as the monkey tapped its fingertip systematically across these gratings, so that it was feeling like narrow gaps and then moving into wider gaps or wider ridges. And so we repeated that same experiment with our artificial finger, and then plotted the artificial mechanoreceptor activity as a comparison against those recordings from the monkey, from the real mechanoreceptor activity from the 80s. And we found something that basically looked very similar for both the slowly adapting and rapidly adapting. You look at the plots, as I'm shown in the 80, and it kind of looks reminiscent, except the key difference is, so maybe like say the A at the bottom is probably the closest match, so stimuli 7, where you can see the peaks and troughs are happening together with the blue and green curves. But the biggest difference is the real skin is more sensitive. So that's why you're seeing kind of, you can see that the real skin can kind of feel narrow gaps, but our artificial skin wasn't able to feel that. But it's basically because it's just not as sensitive as the real skin. But when it can feel it, it kind of acts in a similar way. And then we did a second experiment. What I'm going to do now in a minute is I'm going to skip over about 5 or 10 slides and not discuss the second paper in the interest of time. But so this is the last kind of experiment I'll describe. And then the other experiment was so a kind of a classic test of tactile acuity in humans and animals. Well, this is actually a human experiment in this case. Is to you look at periodic gratings. This is on slide 19. So this is like a set of ridges with like distances between the ridges, and you can have really broad ridges like corduroy, which is obviously really easy to feel, and going down to really really narrow ridges, which is less easy to tell that there's a ridge, that there's a grating pattern there. And then in the experiment, what they did is they randomly gave them at 90-degree orientations to each other and asked the participant to say which orientation the grating was, and then the number of times they get it correct. So on the thick gratings, they get it correct almost all the time. They can tell whether it's a 90-degree, whether it's at 45 degrees or minus 45 degrees, the grating pattern. They can get that. People can get that right all the time. But if you go down to like a 1 millimeter spacing, then people make lots of mistakes, and you get what's known as a psychophysical curve for that, which I've shown on slide 20. So I think the grey plots are from human participants who tried this, so that's the kind of psychophysical curves that they get. So we tried this same experiment and with our artificial fingertip, and we built some kind of deep neural network ways of doing perception of the data, but tried to match it back to the psychophysics, to how humans make judgments. So we used some kind of classic work on decision theory and how perceptual judgments are made on stimuli. And again, we found a match between how the results coming off our sensor and human, and how humans behave on these tasks. So what I'm going to do is I'm going to skip the second paper now, in the interest of time, so don't go on too long. But this is basically all about bringing the second paper is about bringing the vibrational sense into the sense of touch, because I said there's the shallow mechanoreceptors that we're modeling, the slowly adapting and rapidly adapting, but what that misses is the deeper mechanoreceptors that feel vibration and human touch. So what we did in the second paper is we added basically a microphone inside our tactile sensor and used that as a vibration sense, and then we did some experiments to show that you get a kind of a similar behavior. But I'm going to skip over that. So I'm going to skip forward to slide 26, where I'll just make some comments. So I say, to summarize, so paper 1, we showed there's this match between SA1 and SA and RA, mechanoreceptor activity in artificial and our artificial tactile fingertip and real skin. First time such a match has been looked for, and first time it's found. Nobody's looked for it before. Gives evidence that these dermal papillae really are involved in the sensing, because that was the key mechanical structure of our artificial skin that we copied from the real skin. That this whole exercise does not work for, and so that gives us confidence that we're kind of going along the right track with this technology. And then I say the second paper is about the vibration sense, which is also important in human touch and also fits with our technology. But there's a load of open questions, such as what fingerprints are for, differences between human touch and biometric skin. And also, as I said, the skin, we found one of the differences between our 3D printed skin and the real skin was that it wasn't as sensitive. So that gives a question, how then do you make it more sensitive? So I can finish that, but I'm just going to say a couple last words on something I think this maybe will appeal to the audience, because it's, this is on sort of social responsibility in robotics. Or maybe, so I've got a few more slides on social responsibility in robotics, which I can go into, or I could just take questions now instead. So I don't know, what would be better?
Oh yeah, please go ahead, I think, and then we go to the question. Thank you.
Okay, so social responsibility in robotics. So I take open research. I think open research is very important for many reasons, from repeatability of what other people do to just enabling other people to benefit and to develop research that other labs have done. And so I opened up the software that we used and the data. But so in many areas, like say AI, it's easier to do open research because you can just make your code available and you make your data available, and somebody else can download that code and download that data, and they're ready to go. And in neuroscience as well, open research is very important too. And so there, people make the data sets available for other labs to do. Usually, all the equipment they use is off the shelf. So it's relative in those cases. In some sense, the experiments are repeatable by other labs. Although I know that can be difficult as well. So the issue in robotics is that, as well as needing the difference from AI, as well as needing the code and the data, you also need the robots. And robots can be very expensive and dangerous. For example, if you use an industrial robot arms, as we did in this research, they're £20,000 each, have to be installed by highly trained technicians. They have to be screened off because if they hit somebody, it could really hurt people. So that gives a kind of and also a lot of the technology, such as the tactile sensing technology, is not easily available to buy. So that gives an accessibility issue where other labs have difficulty getting that hardware to repeat the work and to develop it. And also, I think because this area of robot dexterity is obviously of a high economic importance as well, that could cause the field to go towards basically private research labs with lots of money are the ones making the advances in this area, because they can have critical mass and the resources to do it, which I think is a danger. It's supposed like Amazon was to own all robot dexterity technology. Is that a future we would necessarily want? So democratizing robot touch, I see, is important for the field. And I mean, here's a few slides. Maybe I won't go through it in detail, but just basically, this is all about trying to make our tactile sensor technology, because it's 3D printed, as easy to make and develop for other labs as possible. That's what this is about. So it's combining the benefits of 3D printing so that other labs can easily make the technology, and combining that with open release of code and open release of the data, and just trying to be as open as possible and trying to make the research as accessible to other labs as possible. So there's a few slides here. So there's some Digitac, which is an open source tactile sensor that we've developed recently, using low cost robot arms to do the research on. So all our recent papers, we've been using low cost arms, which cost about £1,000 or £2,000 when we can, and they're safe as well because they're quite small. But this is an area which is really rapidly advancing as well, and that there's new technology coming out, which is rivaling these more expensive industrial robotics arms in their capabilities. Slide 31, let's say we've done some work on the Synteril that I was mentioning earlier, using these kind of low-cost platforms on these low-cost robotic arms with these open sensors, again, to kind of democratize this technology. And then also, slide 32, another thing, a development we've done in my lab is we've built, there's an anthropomorphic robot hand that's very well known in the field called the soft hand, that mainly at the moment you can buy as a commercial hand, but we've developed a low-cost 3D printed version of it. Also working with the people who developed the hand originally as well. So that's another way of democratizing the field, so that, you know, for a few £100 you can build a state-of-the-art robot hand. So last slide, 33. So for accessible robot dexterity, I see it all about open data, open hardware, open software, and an open attitude as well, I think is the most important. Okay, well, thank you for listening. Hope I didn't drone on too long there. Really like that's
Thank
pretty
you,
funny. Where did you get that slide from?
That was amazing.
I would love
Katarina.
for it when you
That's so amazing, Katarina.
Oh, that's great.
Yeah. Thank you so much for sharing your work, Nathan, with us. I'm pretty sure a lot of us on stage and also some of our newcomers have a lot of questions. So let's see, Katarina, do you have any questions? Serena, Jamie, we'll start with you.
Well, sure. So I'll start off. Fascinating talk and a very fascinating area, and it's so great to see. I certainly applaud your open attitude about in developing it, because so much of the good stuff is, secret sauce to secret places. I'm curious, first about the scalability. You've got the 3D printed technologies, and it's certainly fascinating to look at the human hand and what types of the myriad of applications that we could do.
Yeah.
But in terms of the things that we couldn't do because of scale, so have you looked at how small or how large you could scale up that tactile sense for different applications at different length scales?
Well, that's an interesting question. So the work at the moment in my lab, I mean, we mainly focus on the human hand scale because but that's what we're trying to mimic in a sense. And the kind of unsolved question, the robot dexterity is still a far way off from human dexterity, as it's kind of I don't know. There's the cliche that you can have an AI systems that beat human players at chess, but we're still not at the stage where a robot can reliably pick up a chess piece and move it across a board. So it's completely unsolved problem, or
Mm-hmm.
partially unsolved problem. So we're focusing on that kind of core capability of the dexterity and giving a sense of touch. But I would say, in principle, once you've got a handle on that, once you can figure out how to make the sensors that give the right information and how to train robots so that they can do those dexterous things, pick up the chess pieces and so on, then I see no reason why you couldn't. You're certainly making it bigger. That's it's easier. I mean, the challenge is actually making it small to the size of a human hand. That's
Mm-hmm.
the challenge. So making
Mm-hmm.
it bigger is no problem at all. Making it small is more challenging, I would say.
Interesting. And in terms of yes, sir, certainly there's the control system issues, which those go deep.
Yeah.
But in terms of the actuation, then, do you feel that, I mean, it's almost as though this is pushing ahead of our ability for fine tactile actuation? Do you feel advances in actuation, soft actuation, and fine control
Mm.
are on par, or any comments about that?
Well, there are differences of views in the field on this. So, as you say, there's people who are into soft actuation, so soft robotics. So that would be trying to say replicate, like human muscle, or get, our muscles are soft,
Mm-hmm.
and
Mm-hmm.
trying to get capabilities that are more like that. So that is a completely that's a challenging problem that's still unsolved. But I would say, in terms of having a tendon-driven hand, or using robot arms with motors in, motors are extremely reliable technology. You can make them very small, very powerful. I would say it's there already. And in fact, industrial robot arms are more accurate than human control. As in, you can get like micron level accuracy with those systems, or tens of
Mm-hmm.
microns at least. So I would say the actuation, it depends which view you take, but if you want to kind of classic robot control perspective, and then the actuation is there. But what's not known is the algorithms to then control those robots in a kind of
Right, right,
interactive way with the real world.
right. And so, yeah, just as a final question for me, um, in terms of the whole sensory control actuation loops,
Yeah.
um, it'd be interesting to hear your comments on where we are in the field for perceiving and then planning. These more complex techniques.
Absolutely, yeah. So that's the unsolved problem. Yeah, the sensory motor loop. Yeah, it's not known how to do that in robotics, apart from on very basic tasks. So the work we've done, because it's not even known how to do it without planning. So the work we've done has been on, control, say, without planning, where it's just reactive control that, you might be trying to feel over a complex shape and keep the fingertip, feeling it delicately and staying kind of normal, perpendicular to the surface as it moves, as it slides over a surface, or, pushing an object around, so keeping in contact with it, or maybe molding an object, or deforming it, squeezing it. So those kind of non-planning based tasks, I say, are getting, well, we can do that now using deep learning, and so they are getting solved. Bringing planning into that as well. I mean, because it's not even known how to do the reactive tasks fully, there's not so much done on the planning, apart from in robot vision. So a lot of robot manipulation and robot dexterity work, the vast majority, actually uses vision, not touch. So touch is very much a minority field. And in vision, then planning is really important, and a lot is known there. That people know how to guide arms in a way that they can plan to like move around obstacles, and so on.
Thank you.
Thanks.
Fascinating.
Thank you so much, Nathan, for that. Jamie, you have any questions?
I had one. It's a kind of curious one, really. Right. So, this is incredibly fascinating. That is an amazing talk, and I actually really, really enjoyed your social responsibility
Oh,
talk after it.
thank you. Thanks.
Yeah, that seems really, really important in something like this. What I was wondering is, at the moment, are you more just kind of seeing if it can be done, or do you have any like applications for this? So I'm thinking of how and when tactile stuff for these machines might be kind of useful, right? And I'm thinking there could be applications, but ones that people would maybe not like welcome. Yeah, I was thinking of stuff
True.
like a hand that gives massages and stuff like that. But yeah, have you got any thoughts on that?
Well, I tend to have more of a focus on the industrial side of things. So I mean, the big research institution, Google, Amazon, Dyson, these will all have large labs working on robot dexterity, where to a large extent we don't actually know what they're doing, but they're doing it because there are concrete applications of the technology. So for like say Dyson, they're quite open that they're working on these technologies because they want to have domestic robots, so an extension of vacuum cleaners, but instead something that can pick up, stuff around your house, tidy your house, or load your dishwasher, so on. So they see these as big areas. Amazon is interested in it because it could transform the logistics industry. At the moment, a lot of packing in supermarket warehouses and say Amazon is actually done by people, because robots don't have the skill to be able to put things reliably into boxes and bags. So that they for sure have got programs where they're trying to automate that, so they could have all completely automated warehouses or supermarkets, getting goods to your door. So and these are big economically important problems to solve. So I guess in relation to the open access of the technology is, so my feeling, so I feel that the technology could have a lot more broader benefits that might not necessarily have so obvious and economic impact at first, but still are nevertheless important to do. So I think recycling is an important one. Just being able to, with recycling is basically down to sorting out different materials from each other, so that you're able to recycle cardboard or extract valuable materials from it. At the moment, it's all done by hand. A lot of it by people, and then they find out that a lot of it's actually just burnt. Whereas if you could have robots that are able to do that, that could really transform recycling, really make a difference, I think. And then there's other applications, assistive robotics and helping people. But I think some of these ones that don't have big economic benefits but are still societally important can only really happen if the technology is accessible, so that people can, get something that works maybe as a trial and then develop it themselves into a viable technology for assistive living or for recycling. And so that's why I really think this kind of low cost, democratized open way of doing the research is important, because it enables other people to then take that technology and develop it into something that's of benefit, when there might not necessarily be a clear economic case for it, to start with.
Oh, absolutely. I'm totally with you there. That's actually fascinating. Yeah, there really is quite a lot of possibility. It's such a strange thing, eh? Like, I mean, it's something that everybody would pursue to see about, given like touch, skin, and everything. It's one of those things. It's like, how can we use touch? You don't think of touch, right? Sight makes sense, sound makes sense, and you have to kind of go, what would you use touch for? Thank you for asking my question. Answering my questions. Thanks.
Yeah, but the answer is anything we use our hands for. Robot hands could be able to do that as well if they have a proper sense of touch.
Yeah, thank you so much for answering that. And Jamie, thanks for that question. We have some people on stage, so I'm going to go to Ali.
Oh, cool.
Hey, Katrina, thanks a lot for the opportunity. And thanks, Nathan, for your
Thank you.
great talk. It's really amazing.
Thank you.
I have a couple of questions. I remember one of our colleagues at MIT in the Department of Computer Science, they developed a soft hand from, as I remember, silicon rubber, which
Yeah.
could, in their system or in their developed hand fingers had sensors which could detect the shape and size of the objects, and also it could detect the material. I'm not sure about how it was able to detect the material, and just I would like to know, for example, in your developed system, how this kind of selecting objects or interacting with objects, picking them up, work. Or also it can detect materials or not, or if yes, how it works.
So I know there's a few kind of soft hands out there in the field, and I say we work on soft hands ourselves, with the Pisa IIT soft hand that was developed by Antonio Beakey originally. So if it's feeling kind of shape of an object, or compliance, you can get a lot of that information from proprioceptive information, which is basically how much the motors have moved on the hand. So basically the pose of how much the fingers have moved. You can get a lot of information that way. So it's possible that soft hand from MIT used the proprioceptive information. Now, in terms of like the roughness and the texture of materials, that would require a sense of touch, but that can also be done from a vibrational sense. Um, Now, for dexterous manipulation of objects in hand, so that, tool use or handling a fine motor control of an object, what you need is a high resolution tactile sense. So you need, a lot of high resolution spatial information about the contact in order that you can do fine control of that contact. So I would suspect the hand that you're talking about doesn't have that sense in it, because I said there's only a few labs that work on this. And I say that's the novel, one of the kind of selling points of our tactile sensor, that it does have that high resolution sense that I think I see as key for dexterous manipulation.
Okay, awesome. And you talked also about contact. So between the the different parts of the finger, we have we have contact, and sorry, and in those areas, or in the contacting areas, we have friction, and it may result in adhesion. So have you also considered this kind of failure?
Absolutely. Yeah.
Okay.
Now, this is a good technical question. Yes. So one of the, so evolutionary speaking, in terms of our human hands, the human sense touch, one of the key capabilities we have is feeling frictional information and also detecting slippage. So if you like, a function of our hand is when we're holding objects, we don't want to drop them as well. And you can see why that's important, evolutionary, because imagine like monkeys in trees or something picking apples, you don't want to drop the apple. So having this kind of capability to detect when an object is about to is about to slip, when you're about to lose your grip, or an object is about to slip, which basically comes down to frictional properties, is really key. So it just turns out that one of the rapidly adapting sensors, the mechanoreceptors I was talking about earlier, turns out that those are key for detecting slip, and that our sensor, just the mechanism of it amplifies slip detection. So we have a number of papers on this, where actually it just turned out although the sensor was designed originally for things like edge detection, when we tried it on slip detection and kind of feeling friction tasks, it worked really effectively at that. And we think that's basically down to we were copying how human skin works, and human skin is very effective at feeling slip.
Okay, great. And I have two more questions. One gets back to the structure, and the other one gets back to the properties.
Yeah.
So we have an approach called ICME, and in the frame of ICME, we try to develop process, structure, property, performance relationships. And also for AI, I'm talking from the engineer, material science physics side, not from robotics side. So we try to control. We can develop, even if we go to the data-driven based models, or AI models. What you also developed, we can have, for example, we can develop our models where the input comes from process, and the quantity of stress, quantity of interest comes from the property. Or we can develop a multi-scale model, multi-scale. I'm not sure if it's a good or correct word here or not, or a multiple scale model, like creating a relationship between process, structure, property. And from there, we can see how we can control the, for example, our 3D printing parameters, to be able to control, for example, the structure. As you mentioned, it should be very high. We should have a very high resolution, in the structure, and also from the other side, the property of interest. So in your work, also, have you developed such a relationship between these three steps, or only you consider process property or structure property? I'm very curious to know how it worked.
Okay. I'm not so familiar with process theory. So is this? Do you mean this is this in terms of designing
Yeah, like for
the
example,
sensors?
hatch spacing, heat input, energy. That's what I mean. The velocity of nozzle.
Oh, I see. For the 3D printing, or we just use the 3D printers as it's kind of standard. I mean, we have quite an expensive 3D printer, a Stratasys multi-material 3D printer, so it can do both soft and hard materials. But we don't, go beyond, the standard use of that printer.
Okay, I
I
see.
think that answers your question. I mean, we don't have the expertise to do that, or actually we don't need to do it as well, because we're with the printers we have, they produce the accuracy and the kind of prints that we want.
Okay, good. Yeah, I think it can help a lot.
Yeah.
And the last question is about the properties. You talked about pressure, structuring. My question is, when you are talking about the pressure, is it hydrostatic pressure or you are talking about compressive strain? Because in hydrostatic pressure, everything will be in the elastic zone, so then we will be safe. But if we go to the uniaxial, like compressive strain or plane strain or biaxial, we will have also permanent deformation, and it might not be that good for for the safety and functionality of the hand, and we may get some failure. This is one, and the second is, have you done also any physics-based simulation to study the properties? And the third one, also, have you considered impact loading or thermal loading in your system because of the temperature changes in the environment?
So there was 3 questions. So the
Sorry, yeah.
middle. maybe
I
I'll
tried to
answer the
put all
middle
in
one,
one
which I know I
question.
can answer. So on modelling it, yes, we do some modelling of it. It's actually very challenging to model contact dynamics for these. So you can do simple models that do things just like indentation. That's fairly straightforward in pi bullet we use for that, but there's also more sophisticated simulators. What is really challenging is shear force in these things and getting them into.
Excuse me, did you use COMSOL, ANSYS, Abacus, or you wrote your own codes for that?
We've got some work which we've been doing recently using ANSYS, I think it's called, but we haven't used COMSOL.
Okay.
But I'd say the sim to real work all uses pi bullet, but that doesn't have very good contact modeling in it. So we do some stuff for validating the sensors. We haven't done a huge amount of that, but we've done some. But I say most of it we use for the sim to real stuff because we have to use physics-based simulators for that. And then your other questions were, sorry.
About the impact deformation and also about temperature effect.
Temperature, I mean, we don't really pay attention. I mean, the sensors work very accurately, as in just under uncontrolled conditions in terms of temperature. Just in the lab, we can get down to like tens of microns, like accuracy for feeling, for feeling pose of objects or shape of objects. So. And we can even one of the tests we've done recently. We can like ultrasound using ultrasound for haptics. We were able to map ultrasound fields which only deflect the sensor by a few microns. We're able to detect that. So I don't know if that answers your question.
Because when the robot works in cold
So,
conditions.
Ali, we could possibly come back, but why don't we give
Sure, yeah,
some
I'm
other people
done.
a chance?
Yeah, I'm done. Just I have a quick suggestion. That's I'm done. So about the COMSOL is developed for linear problems, and if you look for nonlinear problems, I suggest to move to Abacus or ANSYS, just as a last suggestion. And thanks, Nathan, for for your answers, and best of luck. Thanks.
Yeah, thank you. Yeah, cheers. I think we are using ANSYS. One of the PhD students has been. I mean, it wasn't my idea, but so I mean, you're absolutely right there. I think. Thanks.
Thank you so much, Nathan, for answering those questions. So next we got Arvin.
Cheers, can you guys hear me?
No, your audio sounds weird.
Okay, sure. Hear me now?
Yes, much better.
Yes.
Okay, cheers. Thank you. So I just have 2 questions. The first question is, what are the uncertainties that you encountered when designing or modeling this stuff? Uncertainty in the sense, say, for example, if I am designing a wind turbine, the velocity is an uncertain factor. We don't know what the wind speed is going to be, right? So in accordance to that, what are the uncertainties that you kind of model, but you didn't have any choice to sort of nullify them or avoid them at all?
So uncertainties.
Right. Okay. So okay. Just to add more context, say for example, if you want to determine the fatigue or the life of the sort of 3D printed hand that you have designed. So what would you go on about, right?
Yeah, I mean, we're still at, I mean, I would say we're at kind of TRL3, so we're not necessarily, trying to develop these things as a product. So, I mean, in terms of the lifetime of the sensors, generally we break one ourselves by having an accident with them. I sat on one the other day and broke it. then the wear and tear on the sensors. So I mean, in terms of the uncertainties, I mean, I would say the uncertainty is the nature of the stimulus, because our sense of touch, it can feel such a wide variety of things. It's almost like a visual sense in our fingertips. So the completely unconstrained nature of contact, I would say, is the biggest uncertainty. If that answers your
Yeah,
question,
right.
probably not.
Yep, that definitely does. Coming to the second question, which sort of derives from your answer, right? By any chance, when it comes to sort of like making the hand feel different surfaces or profiles,
Yeah.
did you and your team get in touch with, say, a metrology department to get an overview or an analog of how profiles work and how to characterize them?
Yeah, so this as you're absolutely right that this area is very close to metrology, so that's measuring things. So we have looked at that, and we have been in contact with companies that do metrology. One of our I wouldn't say competitors, I would say kind of one of our other groups in the field who works on a closely related area is known as the Gel Site Group at MIT. So they also have an optical tactile sensor that uses a camera in it that's high resolution, but it's not biometric. It works more like the human vision. It works more like vision, whereas I say ours is high resolution but is biometric. It works more like human sense touch. So the gel site sensor, which I say is developed at MIT around the same time as our sensor, Meta, Facebook Meta, they have a team of about 10 people who are developing that as well. So that there's a lot of interest in that technology. And GelSite as a company, their principal application is actually in metrology, because people buy it to get very, very precise measurements of contact shape. But I say our sensor, we haven't really looked at that application of it. We kind of leave it to the GelSite people. Our application is more towards, I say, robot dexterity.
Right. Geez, yep, that answers the question. Yeah, and yeah, it was a wonderful talk, and I thank the panel for having me. Geez, thank you.
Well, thank you. Thank you very much.
Thank you so much, Arvin. Finally, we have Eli. Hi, Eli.
Hi, thank you. So, I didn't realize that collision avoidance was still such a problem, especially to the level of being a safety issue. I'd kind of like to suggest a different biomimetic approach, putting piezo electric sensor whiskers along things, because it works pretty well for cats. And similarly, as a person with body hair, I have noticed that like when I'm doing like close order manipulation work, just the feedback from like hair on the back of my fingers or the back of my hand can help, like, know where I am when I can't see what I'm doing. So just a
So
couple of suggestions there.
Well, I agree with you entirely. I mean, I say my background was I used to work on biometric whiskers. That I had a postdoc for a couple of years working on biometric whisker technology. So I completely agree with you. And it's kind of, things have their uses. So I mean, you focused on collision detection, so and proximity sensing as well, which I'd say you wouldn't use the technology we use as a collision detector or as a proximal sensor. It's a fingertip. So its uses for dexterous manipulation and for holding objects. Um, if you want a proximity sensor or a collision detector, you either go for a tactile skin, which is a different technology, where as you say, like you can have piezo resistive skins. The surfaces of our iPhones, which we're probably all grabbing now, that's a tactile sensor. That's, I think, capacitive technology. So there's tactile skins. You would use that for contact detection, or as you say, you could cover things in whiskers, or there's other ways of doing proximal sensing as well. You can use, infrared and so on. I agree, but say the point of our technology is it's not a skin, it's not a whisker, it's a fingertip. That's what we're trying to do.
I was more thinking for in the context of applications like assistive robotics, for example. So if you had like a robot arm that maybe had fur or something that could detect, the weak contact, you can avoid like hard contact.
Yeah, I agree entirely. Yeah, I say, but it's a different problem from what I work on. That's about making your robot safe around people if you've got a robot arm, and there's many technologies there, from, as you say, contact detection, but the more advanced robot arms now, they have very sensitive force torque sensors in the joints, and so they're able to have what's called active compliance as well. So if you knock into them, they can rapidly feel that somebody's knocked into it and then become more compliant, which is another technology. So there's multiple technologies for solving this safety problem. As I say, my focus is on dexterity and fingertips and hands. It's a slightly different problem, but I
Can
agree it's
you add
important.
sorry.
Sorry.
Can you add LiDAR technology for the safety option? Because
Yeah, well, vision, as you say, vision. There's know where things are in a scene. That's kind of right. It's getting the right technology for the problem, as you say. Yeah, LiDAR, vision. You probably need nested technologies, so vision to get a feel of the scene, or LiDAR to get depth maps to know where things are in the scene, coupled with some sort of skin, or as Eli was saying, proximity sensing. So if the vision fails and the robot's about to hit something, to have that to detect when it's about to happen. With active compliance on the robot as well, in the motors, so that it can detect and react, or soft robotics as well. As we were talking about earlier, soft muscles, they help safety as well, because there's compliance of the robot itself makes it safer around people.
yeah, if I can ask a question, so are you planning, or are you, maybe somebody asked the question, I'm sorry, I had to drop off for a few minutes and come back. Are you using this technology or applying this for paralyzed people? Because I follow Miguel Nicolili's labs work with exoskeletons work, and there was very surprising development that not just it helped people to have like good sensors on the feet, for example. It didn't
Yeah.
just help people have better control, but actually people regained some slight control over their motoric system after like being paralyzed for 15 years. So it's quite exciting. So that's one question. And then the other question is, do you think that soon maybe the robotic hands will be better even than the actual hands, by adding, like, I don't know, you could add sense of smell or detectors of maybe some explosives, you have like, you can have the Addams Family hand walk around and feel their way if there's something toxic, or like something like that. Mines.
That'd be awesome.
Fantastic. Yeah, fantastic. So two quick. I'll answer the first one, which is on rehabilitative technologies and exoskeletons. Yeah, and for sure, I agree entirely. So a lot of people in the robot hand area focus on prosthetic hands. So replace it, become Luke Skywalker hand or something. So I personally think that is missing. So the bigger problem, as you've rightly said, stroke. There's not that many people with missing hands and limbs compared to the millions, tens or hundreds of millions of people who've had stroke and have got loss of function in a limb, or in half of their body, or even up to paralysis. Like chronic injury causing paralysis. And you're absolutely right that there's studies that show that if people can have rehabilitative technologies that, for example, might, as they try to move their arm, but maybe they haven't got enough strength to move their arm, but they have an assistive robot that can then move their arm, but under their volition, but is kind of helping them. Then it helps them recover from these injuries, from stroke. So it's a really important technology in my view, and fundamental. I think that so the technologies are getting there, but they're still quite primitive. And fundamentally, what's needed is for those exoskeletons to be able to feel the motion of a human and move with it. It's kind of like if we were to hold, human people doing rehabilitation. I forgot the name of this. Physiotherapists. They might help. They might hold a person's limb and guide them as they're trying to rehabilitate them. So I think that technology could be game changing, and it's another dexterous manipulation problem, so that you have a robot that can act safely with a person, and act as a kind of robot physiotherapist. And I do say that as an implication of this type of technology, and that's one of the kind of examples earlier where there may not be a huge initial economic benefit for it, but there will be people who are highly motivated to try and tackle these problems if the technology is available to them. So yeah, I do see that as really important. And then the second question was, can robot hands be better than human hands? Well, as you say, I mean, I think there's ways that people can think of, once technology is available for people to experiment with, they can think of, ideas that, I could never imagine, or roboticists could never imagine, to make them better. But in terms of the capabilities of robots anyway, so, our sensory motor loop, from, tactile sensation to our brain interpreting that information and then sending it back to our muscles to move, takes roughly 100 milliseconds. So that's quite a slow feedback loop. Robots can operate on a millisecond. They're 100 times faster in how they can, process and control the stuff. So I think that what they will quickly, once you're able to get this artificial dexterity of human-like levels, it will quickly just go past what we're capable of, just because the machines are so much more powerful and can be so much faster and responsive than our own, limited, motor systems.
Another artist field going down the drain. Piano players, violin players. There was a joke.
I just totally thought piano. Just as you were talking about that, I was still thinking piano.
We can now compose maybe 5-hand plays and like attach them, and the brain that's the best at integrating 5 hands will win the competition.
Absolutely. So humans couldn't even play it. Absolutely. But I mean, I would hope that humans would at least be able to be, there'd be something more human about how we play an instrument, and I hope that would be possible to still hear. Hopefully.
Well, but
I
it
did
will be
have
really. Oh yeah, go ahead. Sorry.
I did have a follow-up question. You you gave such kind words about the openness. I'm wondering, for the home enthusiast, the Raspberry Pi, Arduino folks, how would they approach, adopting your sort of starter kit, or getting a hold of some of the advances that you've made, and start looking at novel control systems for this technology?
Yeah. So, well, I mean, I spent most of this week tidying up stuff to put on GitHub. All the CADs, all the software, because it's something. I mean, it's been actually hard work from my own perspective, just trying to bring these things together. But I do strongly believe in it, so I've put a lot of work in it. So I say it's all there. It's on GitHub. Somebody can download it. Somebody can install the software. Somebody can, if you don't have a really good 3D printer, you can send them off by mail order. You can get stuff 3D printed by mail order that costs like maybe £20 or something and delivered. So it's possible to do all this from the home. And actually, in lockdown, I bought a load of equipment so that I could do this myself, just to test this out. And I managed to go through all the steps myself. And now, in terms of like investigating the robot control, I mean, so the robots we're using now, these DoBot robots, which stands for desktop robot, that are made in China. you can buy one of those for £1,000, and a really good one for a couple of £1,000. And I say we can do state of the art in terms of research that's state of the art in our lab. We can do it on those. Yeah, so for a couple of £1,000, you can kind of get everything that we use in our labs for publishing our most recent papers. Now I realise that's still a couple of £1,000, so it's not democratizing it maybe for the home market, possibly for the educational market it fits, but for the home enthusiast. But there's a big home maker community in making robot arms as well. So there's designs up for, a couple of £100. People make robot arms using Raspberry Pis and, laser cutting bits of wood or plastic to do it. So there's a huge maker community in it. I would see this as completely compatible with that maker community, because it's all off the shelf stuff or things that can be just made by a 3D printer.
May I ask, you were talking about maybe having to look at how we make the skin and everything more sensitive, and wondered, like, how do you think that could happen? And I was even wondering, do you think this might actually lead into giving it its own sort of what do you call it, the neurological system?
Well, I mean, so we've got ideas ourselves about how to make it more sensitive, and one being just basically printing it at a finer resolution. The dermal papillae in our artificial skin are a lot bigger than the ones in real skin. So we're currently just pushing at trying to make the skin thinner, 3D printed skin thinner with the smaller structures in it, in the hope that will give more sensitivity. And we expect it will. But I think there's room out there. If other people can try these things and innovate, I think there's room for more innovative ways of doing it that we couldn't imagine in our lab, but other people could look at it in a different way.
Absolutely, so much potential. Thank you so much. This is amazing.
Yeah, I have another,
Thank you.
crazy weird, but it would be an interesting, also basic research question. Did you ever or think of attaching these, let's say, a hand, with 5 fingers to a rat and see if they, their neural system can take, because I'm thinking of this because Miguel Nicolelisi took like infrared sensors and hooked them up to a mouse brain, and the mouse brain was perfectly fine taking care of that sensory input additionally to their regular whisker sensory input. So it would be really interesting if they would be able to like use a hand like we use, and then we have rats running around being able to flush the toilet.
Well, we wouldn't need robots around our houses then. So what's my view on this? Because I have kind of thought about some of these things. So my fear. So there are experiments being done in states where you've got monkey, direct neural implants, electrodes into monkey brains, and the monkeys being able to control like robot arms from just directly from these from these invasive electrodes. So for sure you can do this kind of neural interfacing. My feeling is rats would be good at rat-like things. So for feeling things that are feeling enclosed spaces and going down little tunnels and rusting around kind of things, the kind of things they use their whiskers for, they'd be really good at that. If you got and if you got other sensory information that's a bit like whisker information coming in, then they'd maybe be able to make use of that and do things. I don't think they'd be able to use hands. I think for that you're going to need an animal that's already got hands. So you're up to basically monkeys are the primates. They've evolved to make use of their hands, and so you're going to need an animal of that kind of with hands to make sense of it. That's but that's just a hunch.
I'm not sure because the infrared signal, the mice were able to accurately their cortex was able to accurately use that information and then sense like whenever an infrared signal would come, when they would press a lever or whatever and get like a reward. And they were very accurate in using that information. So apparently the cortex is able, it's kind of this very structured is kind of like a simplified algorithm that can like calculate a lot of stuff, not just it's the input is basically restricting the cortex, not really that the infrastructure of the cortex is restricting what inputs they can take care of. At least that's one of the results I think it points towards. So it would be just really interesting to have like maybe a finger for now. Would be cool.
Well, I agree. So a finger, yeah, I think. I mean, you're talking, sort of sensory cortex. So this, and I agree entirely. They could make sense probably of the sensory information if it was fed in from one of the fingertips. Because they have a sense of vision as well. I mean, it's not very good in rats, but still they've got a sense. So I expect they would be able to make sense of high resolution contact information. What I was thinking they might not be able to do is, if you try to control a full hand, that's a really challenging motor task to be able to use a hand usefully because it's such a complicated device. I kind of think, in primates, they've kind of evolved to, there's enough brain in a primates have quite big brains, probably partly because that cortical material, motor cortical, and pre-motor cortex, so on, it's probably needed to be able to control something of the sophistication of the hands that they have. But that's just a guess.
Serena, don't you have like a glia? If we would add some human glia, it should be.
I was trying to avoid it, but yeah, just well, let's let Bobby. Do you have a question, and I could come back and get into astrocytes.
Sure. Yeah, my question is really quick. First off, Nathan, a quick compliment to your PowerPoint slide deck. It's it's very intense. There's so much material going on. However, at the same time, it's like really well organized, and it kind of interests me to read your work more closely. So I compliment you on that. Like, it's just like a really nice slide deck. Yeah.
Thank you.
Are you or any colleagues? I know the scope of your work, as you mentioned, is kind of refining the 3D printing and what you have already. But are you at some scope, either yourself or just any neighbors in our community, looking at synthetic fascia, like the layer underneath the skin, like recreating that?
The fascia.
Yeah, like the collagen. It's like sheets of two-dimensional, so to speak, sheets of collagen material. And I was actually just thinking about it today, leading up to your talk. Maybe like Twistronics uses sort of graphite sheets at different angles for different electrical properties. So I don't know if anyone in the community is looking to like create synthetic fascia with some sort of mechanical material.
I don't know. I mean, I have to be honest. I don't know a huge amount about fascia. I mean, I would say the adipose layers, as that's kind of mimicked, but the fascia. I mean, is it involved in sensing? Would you say the fascia?
Yeah, and I've really been learning more and more about it since the end of 2019 or mid summer of 2020. But even in like athletics or human health or human mobility, robotics, like so to speak, it's kind of it's an emerging part or organelle, like organ in the body that's being studied more and more, and like there are more properties being discovered about it. So I don't know how much on like the actual like robotic side folks are trying to recreate it, because on the human side it's an emerging phenomena, like biologically or physiologically.
I think I get you now. So I had some physiotherapy recently on my calf, and the physiotherapist ran some weird metal tool down it and said, "I'm scraping your fascia," and I think that's what you're talking about, isn't it?
Exactly. Yeah.
So I'll be honest. I'm completely. I don't know much about them. I mean, actually, the physiotherapist is that's the only time I've heard it before. Um, I I don't know what their role in human contact sensing and human perception is. Um, um, but as you say, it sounds important for things like rehabilitation, and so basically, I don't know, and certainly, given I've got some biological knowledge as well about how the human sense of touch works, and I've never read anything about fascia in that. For sure, because I would say that nobody in robotics has even thought about it. It might be some people in biology have thought about it, but nobody in robotics it's even came up, I would have thought. So I'd be interested.
Interesting.
If you've got any ideas on it, let me
Yeah,
know.
yeah. Maybe it stays an open area. However, I do like what you mentioned there about the 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 homework. So basically, you've done on sensing and touch. It didn't include the fascia, so I'll definitely read up more about it. And if I have any ideas or anything new, I'll reach out to you.
Cool, fantastic. Thank you.
Awesome. Yeah. Just throw something random out there. Thank you for taking the time to go back and forth. Appreciate it.
Thanks. Brilliant. Thank you.
Well, so I guess I want to come to the point of asking you. We've been going for about an hour and a half.
Wow.
How much longer do we have you for before we sort of pop a dimension and get into more elaborate control systems?
I mean, I don't need to go now, but equally well, I don't want to keep you all here if you've got other places to be. So.
Oh no, it was just a chance to see if you have hard stops, or if just curious to ask if we have you for longer.
Yeah, no, I'm still here. Yeah, I'm not being dragged out yet, I think.
Okay, well, great. Because more elaborate control systems is a deeper interest of mine
Okay.
and many people in the field, obviously.
Hmm.
So I'm curious. You've focused on getting precise sensory detection out of a fingertip.
Yeah.
Have you, in terms of multiple fingers, or at what point you might go to two fingers and start coordinating the perception of what those two fingers might be in contact with? Um, have you cracked work on that, or is that something that you're really not there yet, because there's so much more to do on the individual fingertip?
That's the ongoing work that's in my lab at the moment. So a lot of this isn't published, but we've got, I don't know, 4 or 5 different projects where we're looking at multi, multiple tactile sensors, and we've got various robot platforms. We're doing that. One that we've been doing a while is that because we integrate the tactile sensors as fingertips on robot hands, and
Mhm.
we've got various robot hands we use with 2 types with basically 3 fingers, and then we've got the other one, the PISA IoT hand, which is an anthropomorphic hand, so it's got 5 sensors on. So it's kind of more basic tasks we're doing there, like sort of recognition or slip detection, object recognition. Some of the recent work we've been doing is sort of trying to hold an object gently. So using the sense of touch to gently hold a kind of conform, a pliable object. That's some of the recent work, but that's been not on dexterity as such, but more just kind of basic control of the hands. And then in terms of the dexterous manipulation, fine control using multiple fingertips. So the way we're going at this is we're basically using multiple robot arms together. So each robot arm is kind of like a giant finger, you could think of it as. So we've got some platforms where we've got 2 robot arms together, both with 2 industrial robot arms. We've got one where we've been pushing at that and doing various things using those together, and also we're doing it with a low-cost robot arms as well, using 2 of those together. But that's ongoing work at the moment. But it's really the frontier of where we're trying to push it at.
And when I'd be interested in here. See, you were introduced with a neuroscience background. You sort of went through that
Yeah.
tour. I'm curious, in the field of AI, to hear your characterization of what's lacking in more
Uh-huh.
generality, as in context to the problems that you're currently focused on. And I certainly have my own opinions about this, but where would you say the real deficiencies are in the current and contemporary approaches to AI when it comes to the kind of problems that you're looking at?
Well, I mean, I think there's several issues with AI, but the most important in terms of its direction of travel. But for me, the most important one is most AI research is non-embodied. It's all done inside the computer.
Mhm.
It's not in the real world.
Beautiful. Yes, the embodiment. I always thought that's such a critical piece, and I've often thought that we're not going to get real general intelligence without a body in that
Yes,
sense.
I agree 100%.
And yeah,
Sorry.
yeah. Oh, no, no, no. Great. No, this is great. Because there's just the realities of that, of closing that sensory actuation control loop.
Yeah,
Um, provides unique aspects that have to be dealt with. And in
yeah.
terms of how you're approaching that, though, could you tell us a little more about some of the insights of where you would take those approaches in closing that uh, sensory control actuation loop in real time?
So I guess I'll answer the question in a minute, but I was kind of say, because there's a view in AI that if you get better and better simulations, they can approximate the real world, and so why could you not develop some kind of general intelligence in that simulation? But I personally believe that's wrong, because
Hmm.
simulation can never. There's this saying, simulations are doomed to succeed. You can never capture the intricacies of the real world in simulation. I strongly believe that, and I think in robotics as well. I do not believe in simulation only robotics. Robots just in simulation. I believe any work in robotics that is simulation, it must have a real robot as well. I strongly, and it relates to the embodiment. So that's my rant on that. but on how that relates to, I guess, the path for working towards more. How do you bring in knowledge from biology or human intelligence into AI? I guess where I came from, actually, because I came from biology into robotics, my motivations were actually to understand human intelligence, and I saw the embodiment of the human hand and the human sense of touch as a key way of testing, developing, and looking into how the kind of capacities that human intelligence would need in order to use those devices. So that was the motivation for me. Um, uh, But what's happened is the I've kind of drifted away from that, because actually the problems have come down to kind of control problems, and then deep learning came along, which came along after I got into the field, and has really kind of transformed certainly in my lab, but also in lots of other labs, the capabilities to make sense of this tactile information to control these hands. So I've kind of got that's where my focus is at the moment. But I do believe that by kind of getting on that handle on how in robotics you're able to solve these problems of the sensory motor loop and fine control and dexterous use of robot hands, when answers come out of that, which it's not there yet, that will give a route. You'll be able to feed back from that. That will give a reshaping of artificial intelligence, because artificial intelligence can be part of that progress. That could give a reshaping of artificial intelligence, that could give a better platform for studying embodiment and actually dealing with embodied AI properly.
Hmm. Because
Did that
well,
answer?
so
So,
it does, and you may have guessed I'm kind of nudging us in a direction here. Um, because one of the interests that I'm looking at recently in terms of more recent developments in neuroscience and how we
yeah.
might apply them to AI has been looking at what glial structures and astrocytes in
Mm,
particular might be doing with and for neural computation,
mm,
and part of that, what's I'm finding quite interesting is how they've been known to, or more recently appreciated to drive neural synchronous firing
mm,
and bringing together many distant groups of neurons in more organized and synchronous behaviors. And I'm wondering if you're familiar with any of the the recent work in and have thought about that in terms of more detailed control systems for your work?
So it used to be something that I was kind of more familiar with when I was working in computational neuroscience and for a long while. But I say I kind of drifted away from it. But maybe the way, maybe to fit in with your idea, perhaps the way the field goes is, imagine first of all you start doing more. I mean, this could apply to AI and computer vision as well, deep learning and computer vision. Suppose you start pushing these
Mm-hmm.
forwards, solving these tasks with conventional neural network methods, and then there's questions. Can you then use neural networks that are more similar to the structures in the brain? Can you take more inspiration from brain structures? And I think in particular it's kind of identifying something that those neural networks aren't able to do well, and then finding some structures in the brain or some functionality in the brain that you can kind of feed into them and would allow them to solve problems that you couldn't do otherwise. And it may be some analog of the glial structures, or some some large scale synchronicity. Some it sounds like they label a kind of non-local structure, whereas most neural networks, as I understand it, are very local in their computation. So maybe that will become important.
Well, yeah, it's interesting because the models need to improve in both directions. We need much better
Yes.
models of neurons, and and what's going on in there, to the synaptic level and in the dendrites
Yeah.
as well. But then, and of course, there's practical barriers to that in terms of the models are going to get much more expensive
Yeah.
very quickly. But in terms of the astrocytes, they connect and modulate at the synaptic level, but have a syncytium where calcium waves will coordinate over very
Mm.
large spatial dimensions relatively to harness the synchronous um, firing of those neurons. So it's really that dialogue between
Mm.
astrocytes and neurons that is becoming more prominent in understanding the higher cognition. So looking for ways of approaching that in modeling, but then having that approach first in simulation, much to your earlier point, but moving that towards physical embodiments that
Yeah.
can actually bring the real time feedback and into the picture.
Yeah.
And hopefully that
Yeah. I
can
think.
spawn development of more neuromorphic hardware
Mm.
and these types of more physical systems where we can leverage natural computation in that loop.
Absolutely. I mean, I know of people who are working on, neurotransmitters and so on, and, and they're kind of trying to use those as inspiration for improved um, computation in deep learning. And I could see a story as well coming out of astrocytes, glia. I can see how it could fit. Absolutely.
Hmm. Well, Chris, did you have a question? I see you just came on stage again.
I'm curious, essentially, when you're developing some of the touch-related technologies, were there other things that you looked for in the literature, like historically, like some unusual pathways that you didn't actually end up pursuing, but you're like, oh man, if I like quadruple the research funding, I'd totally want to follow up on that thing. What would that thing be?
Oh wow! If I had more money, what would I do? Well, I suppose I've been fortunate for last week because I've got this Leverhulme Leadership Award, so which is coming to an end soon, unfortunately. So I have been quite well funded, um, and in a sense, the way I've tried to take things is actually to make it cheaper to do research because, like I say, I believe this accessibility is really important. So because of that, I kind of purposely moved away from doing expensive research. So, if what would I do with lots more money? Well, I think what the most important thing you could do with lots more money is hire more researchers because I do think, I mean, this isn't there's not a lot of researchers working in this area. So there's maybe 50 PIs altogether in robot touch, maybe a handful, 5 to 10 PIs who work on the kind of high resolution touch like I do. Um, and I do believe some of these problems, to push this forward needs a very large research team to kind of tackle it. So I think that would be the most important use of the money. I would see it as to get more people working in the area.
Would you prefer to have them in your own lab, or just collaborators from other fields randomly working on their own spaces and then kind of bringing those ideas in? What would you prefer?
I would really prefer that other people start developing similar technologies themselves and sprouting other labs doing this. I would obviously like to have a lab that's a reasonable size myself, but I think for me, what actually motivates me far more is enabling others to be able to take this forward.
Very cool.
Thank you.
Thank you so much. I think we've been going for almost 2 hours, and it was such an interesting discussion. And thank you, Serena, for all those really interesting questions. It was exciting to listen to the discussion, and thank you so much for taking the time and coming here. Hopefully you come back one day with maybe updates, maybe some rats with hands. No.
Yeah. Well, I think thanks everybody for such. I mean, it's been a really stimulating discussion, and I've learned a lot, from people's questions. So I've really enjoyed this. It's been an amazing experience.
Yeah, thank you so much. This has been so interesting. I really appreciate your time. We all do. Thank you.
Thank you.
Yeah, and thank you everyone for coming, asking questions, and I hope everyone has a great weekend, rest of Friday, happy Friday. I know your Friday is almost over. And this was really amazing. Thank you so much. We were really looking forward to this discussion, and I think, we had a lot of fun. You seem to enjoyed it, so it was amazing. Thank you, Nathan, and we wish you all the best, and hopefully we have soon a lot of Adam's Family hands running around. Oh, no, I'm kidding.
Okay, thank you. Goodbye.
Bye.
Bye bye.
Thank you. Bye.
Thanks.
Thank you.
3, 2,
Thanks.
bye
Bye
everyone.
everyone.